All right, welcome back everyone. Please let me know if the audio and video quality is fine, and we shall start our discussion shortly. I hope you people are doing well at home. Like I will be waiting here for 2 more minutes, 1 more minute maybe, and then we shall start the discussion here. Yeah, someone is requesting, can I please make the stream on 1080p? Unfortunately, if I do that, you would find something very difficult. What happens is the emulator I use, okay, takes up only a fixed amount of space on the screen, right? So if I stream on 1080p, what happens is the emulator would become very small in the entire window. Okay, so with that said, the fonts will look very small, and there is really nothing I can do right now about it. So that's unfortunately one of the problems, but you can switch to 720p and that would be reasonably good, I think. Okay, and then there is also bandwidth constraint. I mean, I am already uploading at a half megabyte per second speed, right? So if I do stream at 1080p, it might be like 1 megabyte per second stream for me, and for you it will be significantly less. But the thing is, yeah, really, I'm not entirely sure whether it will work or not. In any case, I'm very sorry about that. Just one more thing in the live chat for attendance, please write down your ID or anything like that if you are not using your real name in your Google account. If I get to see your real name in your Google account, you don't have to write anything, you'll automatically get that attendance. I have a Python program that actually does that. Okay, if you are not using your real name, then put your credentials, I mean put your roll number here. All right, so I have waited long enough, so only very few of you have joined. I'm not entirely sure what happened. Okay, I believe all of you knew about the class. In any case, let's start. I hope more people would join gradually. Right, so far we have discussed very basics of assembly language programming, right? Yeah, some of the second year students are also here. Okay, this is a class for the third year students, but if some of the second year students are here, yeah, you can stay in. There isn't any problem. Okay, okay, right. So far we have discussed the very basics of assembly language programming for 8085 microprocessor, right? So again, this is going to be a continuation of that, and this continuation will, I mean, go on for the for the next three more classes, right? We shall learn quite a lot about assembly language programming, how machines, microprocessors are really programmed, right? When we compile a program or something like that, what happens? A machine code is generated on the fly by the compiler, and that is executed by the microprocessor, that is executed by the computer, right? And as such, you can understand that doing these things manually is supposed to give you better insight about the microprocessors, how computers really work. Again, we discussed architecture and so many things in our physical classes. We went so far in our physical classes. Now we are talking about programming here, and we discussed a few things in the last class. Again, today we shall discuss quite a lot. Okay, so bear with me. I won't be probably taking more than 100 minutes. Again, because this is a very complicated class, right? So if I prolong this class longer than that, hardly any of you will be able to understand anything. In any case, let's start our discussion today. We are supposed to discuss a few very crucial points here. Okay, but let's start discussion, right? So before I even write anything on this, okay, can anybody tell me what is the most important register in the 8085 microprocessor? Okay, so if I ask you what is the most important register in 8085 microprocessor, what would you tell me? You would of course tell me the most important register is of course the accumulator, right? The most important register is of course the accumulator. And again, those who want attendance, please write something on the live chat. If you are using your real name, you don't have to give me your roll number. Okay, if you are not using your real name, you have to give me your roll number. Okay, apart from that, there is no problem. Write something on the live chat. If you ask me a question, you will still get an attendance. Right. No. What is the most important register in 8085 microprocessor? Of course, this is the register A or the accumulator, right? Register A, right? Or known as the accumulator. And what is the next most important register in 8085 microprocessor? Of course, that has to be the flag register, right? Accumulator and the flag register, these are the most important registers in 8085 microprocessor. Let me go back to a picture that I had earlier. Okay, and we shall actually discuss the architecture of the 8085 microprocessor in brief once more, so that we have some understanding of what I am talking about here. Some recap of what I am talking about here. Hold on, let me go back. All right, so we are actually talking about this portion, right? So I will zoom in the figure, don't worry. So the thing is that this is the entire architecture of the 8085 microprocessor. We discussed this earlier, right? And in this, you have to be very if you look very carefully, what would you see is that, let me zoom in this. Okay, so this is kind of the internal, this entire thing is a block diagram of the entire microprocessor, right? It contains everything, it shows everything here in the microprocessor, right? Now look at the arithmetic logical unit in the microprocessor, right? In the microprocessor, you definitely have an ALU or the arithmetic logical unit. And again, we discussed the von Neumann architecture. We discussed how these things are connected. Notice very carefully is that we have the accumulator and the flag register, and as well as the temporary register directly connected with the ALU, right? So if somebody asks you what are the registers that are directly connected with the arithmetic logical unit, okay, the answer would be the accumulator and the flag register, right? The answer will be the accumulator and the flag register. These two are the registers that are directly connected with the arithmetic logical unit of the microprocessor, okay? And then the rest of the registers, namely, if I zoom in even further, so the rest of the registers, okay, they do appear inside something called a register bank. Okay, we have B register, C register, D, E, H, L, and then we have some 16-bit registers. All these registers, accumulator, flag register, these registers are all 8-bit registers because this microprocessor has an 8-bit data bus. Okay, so all the registers can contain 8 bits of data. That is how things are designed here. Okay, if the microprocessor is reading something from the memory, it will only read 8 bits of information, so 1 byte of information, right? Similarly, if it writes something on the memory, it will write 8 bits of information, that is 1 byte of information. So all registers are by default 8 bits in nature, right? So accumulator is an 8-bit register, flag register is also an 8-bit register, and then we have something called the register bank. Okay, and inside the register bank you have plenty of registers here. Okay, and registers are basically placeholders, right? You can use registers as variable names for your calculation, for your programs. So sort of. Okay, so they temporarily hold some numbers so that you can actually do some calculations on them. Okay, so we have B register, we have C, so BC, DE, HL. So these registers are individually 8-bit registers, but they can also be combined into pairs. For example, B and C register can be considered to be a single pair known as the BC pair. Similarly, these two registers DE, individually they are 1-byte registers, but they can be combined into a 2-byte register, right, which is called the DE pair. So similarly, H and L, they are individually 1-byte registers, but they can be combined into a HL register pair that will contain 16 bits of information, namely 2 bytes of information. And then we have the built-in 16-bit registers, and out of these, 2 are very important to understand. We have stack pointer, we have program counter. And in the last class we discussed a lot about program counters, how program counter is responsible for actually executing the program, fetching the memory address of all the instructions, right? So program counter is responsible for fetching the memory address of the next instruction. So when we execute a program on a 8085 microprocessor, we give the assembler the initial address, or we give the microprocessor the initial address where the program starts. So we give the microprocessor the address of the first instruction, okay, on the memory bank, on the memory, and the program counter's responsibility is to figure out what would be the next address based on whether the instruction it executed was a 1-byte instruction, a 2-byte instruction, or a 3-byte instruction. Based on that knowledge, the program counter will execute the next instruction, and it will keep on executing unless a halt, hold, or a reset instruction is received. Okay, so we discussed that. So program counter is a very specialized register. And then we have a 16-bit register known as the stack pointer. Now this stack pointer is very important. Soon later on we shall see that this stack pointer allows us to kind of do something like a function call. Okay, all of you have done programming earlier and you know what a function call is, right? So we write a function. So for example, I want to, for example, multiply 2 matrices in, for example, using C programming language, right? We wouldn't probably write the matrix multiplication module inside our main function, right? We would probably write that outside our main function, and then from inside the main function we shall probably call that matrix multiplication module, right? Something like that. So when you write a function outside your main program, okay, if you want to call that, okay, we have something called call instructions. We have call instructions in 8085, and using those call instructions we can go outside the main program module, okay, and call up something called subroutines. Now the concept of function calls was not there in computer science literature back then, so we had something called, we used to call them subroutines, and that name stuck basically. So we have subroutines, and you can do subroutine calls through call instructions, and there the stack pointer would be useful. But if you're not using subroutine call for a moment, you can use the stack pointer as a general purpose 16-bit register. Okay, you get the point. Here we have all these registers. These registers can be individually used as an 8-bit register, 8-bit general purpose register. They can be combined into pairs like a BC pair, DE pair, and HL pair into 16-bit registers. And then stack pointer can be used as a general purpose register as long as it is not being used to keep to execute call instructions. Okay, So soon we shall see that call instructions inherently make use of the stack pointer, and if you are not using that, then you can use stack pointer as a general purpose 16-bit registers. So we have all these registers, and of course we have instruction registers. I talked about the instruction decoder, and I said earlier in the last class that when an instruction is fetched through an opcode fetch machine cycle, okay, the opcode is fetched through an opcode fetch machine cycle from the memory into the microprocessor. What happens? The instruction decoder is responsible for figuring out what to do with that particular instruction. So once the microprocessor receives an instruction, what to do with that instruction, that is decoded by the instruction decoder. Okay. So again, this is a very complicated thing for our course, and of course we don't have it in our syllabus. What I mean is that we cannot have detailed discussion on the instruction decoder. So apart from that, I believe we kind of talked about this entire architecture, how different things are attached to the different portions of the microprocessor. Okay, so and everything is connected to the shared internal data bus. Okay, so with that said, so this is the shared internal 8-bit data bus. Okay, and and of course when data is received or sent from and to the memory device, okay, it comes to the internal shared data bus first, and according by the control and timing logic, they actually are responsible for sending the data to the proper places. So that's the internal architecture of the microprocessor in very brief. I mean, rather the portions we need here. Okay, so here are the registers. So the registers that are directly connected with the microprocessor. So one of you asking that can we consider the stack pointers as not really so. Okay, so the modern microprocessors, all the modern microprocessors, they do support multiple instruction sets. Okay, right? So this all the instructions that we write that we can write for the 8085 microprocessor is known. So if you take a paper and write down all the possible instructions that you can have on the 8085 microprocessor, okay, then you would have something called the instruction set, a set of instructions for the microprocessor, right? Set of instructions containing all the instructions for the microprocessor, right? So you have a certain set of instructions for this 8085 microprocessor. But nowadays, I mean, this is a long, I mean, very old history at this point. This microprocessor was released in 1976. So this is more than 40 years old right now at this point. Okay, so it's a long history, right? Very old history as far as technology goes. Again, we discussed why we are studying this instead of studying something slightly more modern. In any case, all the modern microprocessors, and by modern I mean anything that was released in last 20 years, they support multiple instructions. A single microprocessor, sorry, not multiple instructions, multiple instruction sets. A single microprocessor, I mean released in last 20 years, are capable of executing multiple instruction sets. Okay, so multiple instruction sets. Now you can understand the microprocessor can be told that, okay, microprocessor, I am now pulling instructions from this particular instruction set. Okay, an instruction set is a set of instructions that the microprocessor understands. Okay, independent set of instructions that the microprocessor understands, and all modern microprocessors support something called multiple instruction sets. Okay, and this is kind of sort of a plug-in architecture for microprocessors. What happens is all modern microprocessors come with some built-in programs inside this. Now this entire microprocessor 8085 does everything in a dumb manner. You have internally, you don't have any microcode or anything. Okay, internally you don't have any program running inside the microprocessor, right? Everything is done through logic circuits. Okay, so you have an entire combination of logic circuit here. Okay, a huge logic circuit here, and of course you know that there are 6500 NMOS transistors in 8085 microprocessor. The modern microprocessors do contain way more transistors, but here we had 6500 NMOS transistors, and everything is done through logical circuits. Okay, so you have some logical circuits and everything is done through that. Modern microprocessors often keep things generic Okay, and modern microprocessors do have some programs running inside the microprocessors. Okay, that lets the microprocessor do follow instruction sets. Okay, so you get the point, right? Modern microprocessors do run certain instructions to execute the instructions that the user giving it. So you understand what I'm saying here, right? So yes, everything is very essential. Whatever is here is very essential. None of these is like not needed, right? So you cannot really call it a plugin architecture, but yes, modern microprocessors are. This wasn't, because back then silicon real estate was very important. Was very difficult to get. Nowadays, inside a very small wafer, you can actually put billions of transistors. But back then, it wasn't a possibility, right? It was only a large scale integration, right? We have something like a very high, very large scale integration nowadays, where within a small 1 square centimeter wafer, we embed like billions of transistors. Back then, it was only thousands of transistors. Okay, you get the difference, right? All right. So with that said, let's go back to our discussion here. Okay. So we have the accumulator and the flag registers, and these registers are directly connected with the with the ALU. So when the ALU does some arithmetic operation, 8-bit arithmetic operation, it is very likely, or rather almost a certainty, that the result will be stored in the accumulator. Okay, apart from a few instructions. But whatever the instruction does, okay, the status of the instruction is often reflected into the flag register. We shall talk about that as we need. Okay, so A and F are the most important registers. It's called the accumulator and flag, and combining these two registers, and again, just let me so I have B registers and C register, D, E, H, L. We have stack pointer and we have program counter. So these are the registers you should be concerned about. So these registers, all these registers can be used in pairs. Even this one can be used as a pair. This has a specific name. It's called a program status word. This register is often called a program status word. When it's considered a pair, this is called a BC pair. This is called a DE pair. This is called a HL pair, and these are 16-bit registers nonetheless, stack pointer and program counter. But A and F combined, it's called a program status word, or PSW. Okay, if we want to call A and F in combination, we call them PSW, right? And if I want to call BC in a pair, I would not call BC. Okay, I would just write B, D, H, and the microprocessor, through relevant instructions, would understand that we are talking about the pair of the registers and not the individual register, right? So apart from that, these registers often have some certain different purposes, right? For example, the accumulator has the purpose of keeping the result of arithmetic operations, 8-bit arithmetic operation. The flag keeps the result, the status of the last executed instruction. So when you execute a last instruction, for example, you are adding something, adding two numbers. If there is a carry, that will be reflected in the carry flag of the flag register. Okay. If there is auxiliary carry, that will be reflected in the auxiliary carry flag in the flag register. Okay. If we are doing operations on signed integers, not just unsigned integers, but signed integers, including negative numbers, of course. Okay. If you are doing operations on that, then the flag register reflects whether the result of the last arithmetic operation or logical operation resulted into a negative number or not. Okay. Also, the flag register tells me whether the result of the last arithmetic operation or logical operation resulted into a 0, then the 0 flag will be set. So this is how there are 5 flags inside the flag register. Even though this is an 8-bit register, there are only 5 flags. Okay, and the flags are set and reset based on the status of the last executed instruction. So yes, really, this is the result of this stores. For most of the time, this stores the result of 8-bit arithmetic and logical operations, and this usually stores the status of the last executed instruction. So this is called a program status word. Of course, you understand the whole life purpose of program counter. You cannot directly access program counter. You should not. Okay. I mean, rather, you should not directly modify the program counter. Okay, unless it's really necessary. And the thing is, you do not really want to mess with this program counter. All you need to do is to set the initial value of the program counter, and the program counter takes does the rest automatically. Okay, it is responsible for figuring out which bytes stored in the memory are instructions and which bytes stored in the memory are data, right? Because instructions must be fetched through opcode fetch machine cycles. That's the responsibility of the program counter. Okay, so it has special purposes. Now, this stack pointer can be used as a generic 16-bit register. Okay, it also has a special purpose of pointing to the stack. As the name suggests, it's called a stack pointer, so it points to the stack. So with that name aside, the idea is that this helps us use something called call instructions and employ stacks in our programming. We shall learn that at a future class. But apart from that, these register pairs do not have any special purpose. They are there to be just pretty registers for us. Okay, but this HL register pair has certain special purpose. It can be also used as something called a memory pointer. So this one is called a stack pointer. This one is called a program counter. And I use Indian spelling, not the American spelling, right? So this is called the memory pointer. Okay, this is often called the memory pointer, and we shall shortly see why it is called a memory pointer, right? So before I go any further, let me introduce you to one very important instruction. So in the last class, I introduced you to this instruction. So you had this instruction MBI, for example, B, comma, say for example 56. What happens? So this is one of the immediate instructions, and we shall talk about addressing modes, everything, okay, later on. But after executing this instruction, what would happen? This data 56 will be copied into register B, right? This data 56 will be copied into register B, right? You get this idea, right? All right, so that's understood. So similar instruction to store 16 bits of data into a register pair is this LXI. So if I say LXI B, comma 3, 4, 5, 6, what would happen? So if I say LXI B, comma 3, 4, 5, 6, so after this instruction, when this instruction is executed, what happens? Register B gets a value of 56 in hexadecimal. Now after executing this instruction, register BC pair would get a value of 3, 4, 5, 6. Okay, and of course B register would get 3, 4, and C register would get 5, 6. So that's how you assign a certain value to a register pair. Okay, so this is again called an immediate instruction, and we shall talk about that. It's called move immediate again. So LXI it's the same thing for a register pair, something like that. So if I want to move, if I want to copy a 16 bits of data into a register pair, that's the instruction we use, right? Right? So is there any problem with this? Of course we can do that, right, without any issue, right? So right, so I have a question for you. How many bytes does this instruction take? How many bytes does this instruction take? How many bytes? So can anybody tell me how many bytes does this instruction take? So we talked about how many bytes instruction take at an earlier class. So I want you to tell me how many bytes would LXI instruction take. I did not talk about MVI, okay, LXI. Some of you are saying it's going to take 2 bytes, right? Is it going to take 2 bytes? Someone is saying 1 byte. I mean, my question is, how many bytes would this entire instruction take? Can somebody tell me? Try figuring this out, because I need you people to figure this out. So I will be back shortly. So it seems like none of you are able to figure this out, right? Pretty strange. Okay. So, I mean, what do you see in this instruction? You see an instruction, right? So it must have an opcode, right? So you have this opcode in this instruction, and then you have this data byte for this, right? This is just a data, but data bytes, right? How many bytes does this would this take, as far as the data is concerned? Okay, so this is a 16-bit data, right? So it's a 2-byte data. So I have 5, 6 appearing first, and then 3, 4 appearing then. Of course, through the little endian architecture we discussed in the last class. So how many bytes would this instruction take? Of course, every instruction has an opcode. Now it has a data, but the data of 2 bytes. So how many bytes would this instruction take? Of course, now this is going to be a 3 bytes instruction. Okay, this instruction is going to take 3 bytes, right? All right, I hope you understand this, right? All right, so this is a 3-byte instruction. Okay, so opcode and then 2 bytes of information here. And here we have, for this instruction, we have the opcode and 1 bytes of information, right? So this was a 2-byte instruction, but this is going to be a 3-byte instruction, right? So you should try really your best to figure out how many bytes one instruction would take, right? So that is something we can do, of course, without any issue. But now there is a special purpose, special thing here. Okay, if I do the same thing here with HL pair, if I say LXI H comma, say if I say 3 4 5 6, okay, so if I say just like this one, if I say LXI H comma 3 4 5 6, if I do something like that, then of course same thing will happen. H register will get 3 4 and L register will get 5 6. So this is going to happen, right? Is there any problem? Right, there is no issue with this, right? So H register will get 3 4 and L register will get 5 6, right? Right? So I don't think there is any issue with this. So what is the value of the HL register pair? If you consider the HL to be a pair, that would be 3 4 5 6. Now why are we talking about this? We are talking about this because this HL register pair can also be used as something called a memory pointer. This is sometimes also used as a memory pointer. This is called a memory pointer. And before one of you points out, yes, it is indeed very similar to the pointers you have in your C programming language. Indeed very similar to that. So it holds the memory address to the data in the memory. So what I mean, try to see. Say this is how I draw a memory bank. Let's try drawing it. So all the all right. So we have ants taking over. Hold on, huh? Sorry for the interruption. All right. So so the entire memory of the microprocessor, okay, again, memory is not internal to the microprocessor, is external to the microprocessor, is attached to the microprocessor, right? And the entire memory can be considered to be a series of memory addresses, right? A series of a sequence of memory addresses, right? So the idea is that memory can be considered to be something like this. So you have boxes addressed sequentially. So address would start from 0000 and end at FFFF. So 0000 is the minimum address it can have, and FFFF is the maximum address it can have, because it has a 16-bit of address bus, right? The address bus is 16 bits wide, so it's a 2-byte for the address. So address can start from 0000. So that's the first address. So let's say we are talking about something in between those, right? Something in between those. Say if this is address number, say this is the address number 3450. Similarly, this will be 3451, 3452, 3453, 3454, 3455, 3456, and so on. So that is how addresses are there, right? So so each address block can store 8 bits of information, namely 1 byte of information, right? So with that said, I can have a few more here. So we are just drawing what is there in the memory, right? So and so on. Right. So the idea is that all the memory addresses are sequential in nature, okay, and they can be addressed sequentially or individually without any problem, right? So, and of course they might have some data in them, right? They might have some data in them, right? So now, say for example, imagine in these memory addresses, so for example, imagine in this memory address, in this particular one, I have a data of, say for example, so it's a hexadecimal number, okay. Of course, every number is a hexadecimal number, okay. So say I have this data in this memory location. So what is the address in which this data is stored? Of course, that will be 3, 4, 5, 6. In this address, this data is stored, right? All right. So question is, how do I fetch this from this memory address, okay, into one of the registers of the microprocessors? How do I do that? How do I do that? Do you understand my question? Previously, when we wrote a program to add two numbers, for example, previously when I wanted to add two numbers, for example, if I wanted to add two numbers, some like say for example, so previously maybe I wanted to add two numbers, say these two numbers maybe, right? So previously the code we wrote was something like this. We did MBI A comma FA. So that way we copied the data FA into the register A. Then we did MBI B comma CE. Okay, so we copied the data CE, or let's just use numbers. That might be I mean easier for you to understand. Some of you might get confused. I'm keeping things as simple as possible to the best of my ability here. Okay, say maybe 78 and maybe 39. Okay, so here you would have this, you would have this. So this data would be copied over to register A, this data would have been copied over to register B, and then we did add B. So data stored in register B was added with the register A, and the result was stored in register A. Okay, and then we did something like STA. Okay, and with that, did we do STA? I'm not entirely sure whether we did it or not. Forget that. So that is how we added two numbers, right? That is how we added two numbers. We moved the data directly into register A and copied the data directly into register B and added those two numbers, right? So if I write something like this, what happens? The opcode for MBI A will be directly followed by the data that I want to copy into register A. Then the opcode of MBI B will be directly followed by the data that I want to copy into register B. And then we have the opcode for add B. So that is the instruction, that is the set of the instructions we used to directly embed the data into our program, right? So this data was embedded directly into our program. Right? Do you understand what I'm talking about here? This data was directly embedded into the program, right? So inside the program you have this data, right? But what if inside the program you don't have the opportunity to keep this data? Maybe you have the program into in a separate set of memory addresses, and you want to keep the data separated from the instructions. What are you going to do? So for example, here look very carefully. With this example, I have two separate memory addresses where I have kept the data, right? So you could say, okay, MBI A comma 78. So I have this data copied into this, but no, my job is to figure out. My job is to take whatever data resides into this. Okay, this data could be something like X, I don't know. Okay, and this data may be Y. Okay, I don't know. So I'm writing X and Y because I don't know. But whatever data I have in this memory location, I have to copy it over to register A. and whatever data I have in this location, I have to copy it over to register B. You get the point, right? So that every time I want to add two different numbers, I don't have to rewrite my program. Try to understand. If I write my program this way, what happens? Every time I want to add two different numbers, or if any one of these numbers is different, then I have to rewrite my whole program once more, right? Rewrite my program, right? You understand the point, right? And assemble it, run it. The idea is, now I want to write a program that adds up this number and this number stored in this memory location and this memory location, stored in these two consecutive memory locations. I want to write a program that adds up numbers stored in these two consecutive memory locations, right? Do you understand what I'm talking about here? So that I don't have to modify the program every time I want to change these numbers, right? If I want to add two different numbers, or if one of these numbers is different, then I don't want to modify my program. My program should run unmodified, okay? And it should be able to add these two numbers, okay? Whatever number appears here. So every time I want to add two numbers, all I have to do is just change these stored numbers here, and that's it, okay? If I run the program again, it will add those two numbers, okay? Whatever appears here, so that I don't have to modify my program again and again and again. So this is kind of an easy method, but this method is inefficient because every time I want to modify one of the numbers or both the numbers that I'm going to add, I have to modify the program itself. Now we are going to write a program in which we don't have to modify the program in order to add two different numbers. You get the idea, right? So in order to do that, we should be able to pull whatever is there in this memory location into register A and pull whatever is here in this memory location into register B. We can do that, okay? We shall have to do that, please, okay? That is going to be our task right now. So let's jump into that. So in case if you have any query, feel free to ask, because if you don't ask, I won't be able to tell you anything, right? Because unless I know what your queries are, I won't be able to tell you. So the point is, I want to pull this data, whatever data here there might be, right? Of course it's an 8-bit data, so yeah, 1 byte information, right? So in order to do that, we use the concept of pointers here, namely the memory pointer here, okay? So we have two pointers, one memory pointer, one stack pointer. We are not using the stack pointer right now. We are going to use the memory pointer, but this can be achieved through stack pointer as well. But we are going to use the memory pointer right now. So what we are doing right now, we are using the memory pointer. So I told you earlier that HL register pair is also known as the memory pointer. So what I mean, if I do LXI H, 3456, what happens? The HL register pair gets a value of 3456, right? So if I do something like that, then HL register pair gets a value of 3456, right? All right, HL register pair gets a value of 3456. But the value of the HL register pair is also known as the memory pointer. Try to understand what I just said. Okay, I copied some data into H and L registers, but whatever value the HL register pair gets out of this, okay, for example, the value of the HL register pair is 3456, is also or can also be used as the memory pointer, okay? So we have something called a memory pointer that points into this. So, and the memory pointer in kind of a C programming terminology is represented with M. So there is a temporary register named M, okay, that holds the data pointed by the value of the HL register pair, okay? So whenever, if the value of the HL register pair, I mean this happens all the time, okay, if there is nothing stored in HL register pair, it will be 0 0 0 0, right? But if you store something on the HL register pair, okay, whatever value I have here, it could be 0 0 0 0 as well, okay? Whatever value of the HL register pair is, okay, that memory, in that particular memory address, whatever data is stored is referred to by this temporary register M. It is also called a pseudo register. Okay, in this pseudo register M, whatever value, okay, it's a pseudo register, whatever value of whatever is the content of that particular memory location is actually appears. You get the point? So again, if instead of this, if this was something like, say for example 3451, then this would be pointing towards this. M would be pointing to this memory cell, and whatever value is contained within that memory cell. Okay, do you get the point? So LXI, so HL pair has two different purposes, rather three different purposes. One purpose is that you can use H, you can use L as separate 8-bit registers. The next purpose is that you can use HL as a single 16-bit register pair to do 16-bit operations. Okay, and the third purpose of the HL pair is that it can be used as a memory pointer. So this is the third purpose here. Okay, we are using the HL register pair as a memory pointer, so that I am pointing to a memory location. Okay, so that this points to a memory location, and whatever is the content of that memory location is given through the fictitious register M. Got it? Got it, right? So with that said, so I have this, right? So whatever is the content of register M, that's basically the data stored in memory location 3456. And again, I am monitoring the live chat all the time. So if you have any query at any point, feel free to interrupt me and ask me a question. All right. So earlier, with an example, while discussing opcode fetch cycle in complete details, I had shown you an instruction called the move instruction, right? So what does the move instruction do? Move instruction copies data from one register into another register, right? So I now currently have this data in the fictitious register M. Okay, in the fictitious register M, and I want to copy over this data into register A. Okay, so now what happened? Kind of the same thing happened here. Okay, with MVI A,78, I hard coded the data here. Okay, try to understand. See if this data is 78, for example. Okay, what now happens is that this data is separate from the instruction. This data does not appear on the program itself. Get the point, right? This data does not appear onto the program itself. Okay, so what I am doing, I am pointing the memory pointer onto the address where this data is stored. So what is the address? 3456, at which this data is stored. Okay, so when I point the memory pointer to that particular address, and what do I mean by pointing the memory pointer? Just setting the HL register pair, okay, to that address. So when I set the HL register pair to that address, what happens is that this fictitious memory pointer or fictitious register, okay, points to the data stored in that address. So if I do a move A comma M, what happens? This data is copied over to register A. Please let me know if you understood up to this point. Please let me know if you understood up to this point. All right. So this is a 1-byte instruction, right? There is no data or anything appearing after this, right? So this is a 1-byte instruction per se. But my question to you now is, how many machine cycles would this have? This is a 1-byte instruction, just opcode is there. move a comma m just has one opcode. But how many machine cycles would it take? In the last class, I talked about the move instruction, and I told you that it only has an opcode fetch machine cycle, right? So now question is, will this one have only the opcode fetch, or something else will happen as well? Will this one have only the opcode fetch, or something else will happen also? What do you think? So as far as the bytes concerned, this is a single byte instruction, one byte instruction. But my question is this how many machine cycles would this have? Would it just have opcode fetch, or would it have something else as well? Please do tell me. I mean, what do you think is going to happen? Yes, one of you are asking that this M register only points to the data stored while we. Yes. So if I write something on the HL register pair, anything, intentionally or unintentionally, okay, even if it is 00, when it is 00, the M register is pointing to the memory address 00. So when HL register is 0000, okay, when HL register pair is 0000, nothing is stored, then the memory pointer points to the data stored in memory location 0000, right? So that's always true, not when we do LXI and something like that. No, it's always true. HL register pair, the memory pointer M, for example here, is always pointing to the data stored in the memory address pointed by the HL register pair. Okay, even if you don't want to intend to use it that way, it still is. And only one of you is correct right now. There are two machine cycles here. Okay, the idea is that move a comma m instruction does not have just the opcode fetch. It must have opcode fetch and memory read both. Okay, so that's an exception of move instruction. If I say move b comma a, so we are copying data from register A into register B. Try to understand everything is happening internally. So this would only have, so instead of b comma a, let's write a comma b. That would be nice. A comma b. If I say move a comma b, try to understand everything is internal to the microprocessor. The data is already there in one of the registers. Okay, and we're just moving it into another register. So this would only have the opcode fetch. This is a 1 byte instruction, and this will only have the opcode fetch. Okay, but this instruction, where we are talking about moving the data into the accumulator from M, try to understand that M is just a fictitious pointer here. What is it doing? It is just pointing to the data stored in the memory address. It is not there in any of the registers so far, right? So in order to move this data pointed by register M into the accumulator, the microprocessor will have to do an opcode fetch and one memory read. One opcode fetch, one memory read. Okay, right? So it will have to do the opcode fetch in order to, of course, fetch the opcode. That's understandable. And then it will have to do memory read to read from the memory. Okay, because it will have to read it. Here there is no memory read is there, because there is no memory read to be found here, because everything is internal to the microprocessor. All the registers are inside the microprocessor, right? But this is not inside the microprocessor. The data being pointed by register M, okay, this is just a data stored in the memory device. So the microprocessor will have to read it from the memory. So move a comma m, okay, or instructions like move m comma a, or anytime you have m, okay. So here that's going to be opcode fetch, memory read. Opcode fetch, memory read. Okay, or memory write. So if I say m comma a, it is going to be opcode fetch, memory write. So move instruction is a very weird instruction, we will see. Okay, just to show you, if I say move m comma a, what are the machine cycles would happen here? Of course, the first one would be an opcode fetch. It needs to read the opcode, right? And then what does this one do? This one copies the content of register A into M. Now what is M? M is just the memory location pointed by the HL register pair, right? So it is just like writing something onto the memory. So it will have opcode fetch and then a memory write. So move instruction is a very weird instruction in that sense. Okay, it can just be an opcode fetch if everything is happening internally into the inside the microprocessor, and if this opcode fetch, if this move instruction is reading something from the memory pointer like this, then it will do a memory read after the opcode fetch. And if this move instruction is writing something to the memory pointer, then it will have a memory write after the opcode fetch. So this move instruction is pretty weird in a sense. Please let me know if you understood this, because this register M is not internal to the microprocessor. It is just a pointer to the memory address. Okay, this helps you fetch the data or write something on a particular memory address. Okay, you get the point, right? So opcode fetch has 4 clock cycles, memory read has 3 clock cycles, this 4, this is 3. Alright, so I believe I got that out of the way. Again, if you have understood this or if you have any query so far regarding any of these, please let me know. So now we have this 7, 8, this data stored in register A. Okay, right? Please let me know if you have any query. Alright, so with that said, all I now have to do is to fetch the next data, and that could be anything. Again, let me remind you, what was our purpose? Our purpose is to figure out a way through which, without modifying the program, I can add 2 different numbers, right? With this approach, the approach we had in the last class, with that approach, in order to add 2 different numbers, or if any one of the numbers are different, we would have to modify the program, right? Now here I just have to modify the data here. Okay, the program does not need to be modified. Okay, that is how we are writing a program here. In this case, the program needs no modification if I want to add 2 different numbers entirely. So with that said, all I have to do is now point to the next memory location. What is the next memory location? 3457, right? So my memory pointer needs to move into that memory location, right? So instead of now pointing to memory location 3456, it needs to point to the memory location 3457. So I want my memory pointer to be pointing at this memory location. Yes, I can fairly understand what you're talking about. You have forgotten everything about the clock cycles and anything, all right. So yes, we need to have recap classes on those, unfortunately. Okay, so we can arrange those if you wish. So I mean, of course, I need to have a large enough demand, right? So if only one of you are saying that you need a recap class, unfortunately we cannot do that. And the problem is, I gave you the slides. Try looking through that. Okay, and try going through that. And also Ashok sir has given you the PDF of the book. Okay, try going through that. Everything is explained very clearly. Ask me if you have any query, and then if many of you say, okay, we need an additional class on that, okay, I would definitely arrange one. Okay, describing entire machine cycles once more. Okay, in clock cycle to clock cycle details. Okay, with as much detail as you might need. In any case, please feel free to let me know. Okay, so up to this point is fine, I think. Yes, I do agree that it's better to have a recap, right? Then please let me know. We can have it on next Monday. I mean, yes, I mean at least more than 50% of you should agree that we can have a recap class. Otherwise, we shall move forward and later on we shall go back and have a recap class. All right. So with that said, we have this. So up to this point you understood, right? So now I want my memory pointer to be pointing to the next memory address, which is 3457. So all I can do simply, I can do LXI H, 3457, right? All right, I can do like something like that. I can do LXI H, 3457, just like this one. Now my memory pointer M is now so this memory pointer is now pointing to the data stored in the next memory address, right? All right, some of you might already have figured out what I just did poorly here, right? So this is again a 3-byte instruction, and this has many machine cycles, as I will shortly tell you. Okay, so unfortunately, or rather fortunately for us, we have one instruction that can help us do so. Okay, so we are pointing to the next memory address, okay, which is 3457. The previous memory address was 3456. Now we are trying to point to the next memory address, which is 3457. We can do that by separately assigning the memory pointer a value of HL register pair, a value of 3457. So after doing LXI H, 3457, I have 34 in H, 57 in L. Okay, and of course that way the HL register pair would have a value of 3457. So memory pointer will be pointing to the next memory location. But instead of doing that, since memories are consecutive in nature, we have another instruction called INX. Just like INR, I have an instruction called INX. So if I write INXH, it increments the register pair. It increments the register pair. So if I say INXH, what happens is the value of the HL value contained in the HL register pair as a whole is incremented. Okay, so what was the value of the HL register pair? It was 3456. So it was pointing to this memory location. Okay, it was pointing to this memory location. All right, so previously it was pointing to this memory location. Okay, previously it was pointing to this memory location, and now it is going to point to this memory location because I have incremented HL register pair. So the HL register pair has now a value of 3457. Okay, you get the point. We could have done that by writing LXI H, 3457. We could have done that. Okay, but that would have a bad thing to do because we would have wasted many clock cycles on that. But instead of doing that, we can do INXH, and INXH does our job here. What was our job? To increment this value by 1 because the next number is stored in the next memory address. So I incremented the value of HL register pair by 1. So the HL register pair is now containing 3457. So the memory pointer is now pointing to this memory address 3.3457 where you have this data stored. Okay, now maybe this data is 39 maybe. Okay, now you have to just one more thing, INXH, talking about INXH, or INX, talking about the INX instruction. Okay, INX could be anything, INX B, INX C, INX B, INX D. Okay, if I say INX B, it increments BC register pairs value. Okay, if I say INX D, it increments DC register pairs value. INX H increments the HL register pairs value. INX SP increments the stack pointer. Okay, so if I say INX H or INX anything, it only does opcode fetch. Of course, it only does opcode fetch because the registers are internal to the microprocessor. Okay, so it's not going to do memory read, memory write, or anything like that. So it's going to do an opcode fetch. But this is a special kind of an opcode fetch because this opcode fetch itself takes up 6 clock cycles. Okay, and how do I know? Because I have read the book. Okay, so otherwise there is no way for you to know this, right? INX-H takes up, is a special opcode fetch. It takes up 6 clock cycles. Okay, the idea is out of these 6 clock cycles, the first 4 clock cycles are identical to any other opcode fetch. Okay, but the next 2 clock cycles in this special opcode fetch are undefined, rather a trade secret kept by Intel only. Okay, but the first 4 clock cycles are identical to any other opcode fetch machine cycle. So yes, so it's a single machine cycle, just the opcode fetch, but it's a special opcode fetch that has 6 clock cycles. You got the point, right? So yeah, things are very different, and as you gain expertise on this, you shall quickly learn that there are quite a few things that you need to be able to remember. Okay, now of course, if I do something like this, move I think we are back, and it took me like 20 minutes. So Alan's had some networking issues. So those who are still here, thank you very much for being here. And let me make a phone call, and uh, I shall resume the class in 5 more minutes so that more people can join. Okay, and don't worry, I won't be taking much longer because this discussion was almost going to end like in 20 minutes at that point. So I will try to make it quick and end it slightly in 15 minutes maybe. So please let your friends know that we are back online. Right. This was the longest intermittent network issues I'm having since the lockdown started. So I'll come back after a phone call. All right. So we had a lot of internet issues today. So incidentally, I was talking about the quality of internet right on the onset of this class, that I cannot stream at a higher bandwidth simply because the internet hasn't been great since the lockdown started, and you just got a hands-on example of that. Okay, this is really bad, really bad. And that is one of the reasons why I chose YouTube live streaming instead of doing a class through Zoom or something like that. Because if since this happened with me, I am here to cope up with it. But if this happens with one of you as a student, okay, you won't be able to attend the rest of the class, right? And you would miss the entire thing. So since this is being recorded and being kept on YouTube, you shall be able to follow this at a later point of time, right? Even if your internet connection goes down. If mine goes down, I shall try to cope up with it in some way or the other. In any case, so like I will be waiting here for 2 more minutes so that more people can come back and we shall start our discussion today. It seems everything is working fine once again. So this is the 4th time I am encountering this issue since the lockdown started. So this is the 4th time my class was interrupted because of an internet issue. In any case, let's start our discussion once again. So can you please let me know in the live chat that if everything is fine? Also, please mention it on your students group that the stream is back again, so that they refreshes their YouTube. And it will be available. In any case, if any one of you cannot join, you can come back and watch it later on. So let's start our discussion. Okay. So should I wait for one or 2 more minutes, or should I start then? Again, this entire discussion will be cut from the final video, as if nothing happened. All right, so let's go back to our discussion. As we were talking, let's go back a while. Okay, so as we were talking, we use HL register pair as the memory pointer, right? So we use HL register pair as the memory pointer, and right now, after incrementing the HL register pair's value, the value of the HL register pair is 3457, right? So it was originally 3456, now it is 3457. So the memory pointer is now pointing to this data, right? So the memory pointer is now pointing to this data stored in memory location 3457, right? So now if I do this move instruction once again, move b comma m, so whatever is being pointed by m will now be copied over to register b, right? So what was being pointed by m? This data stored in memory location 3457 was being pointed by m. Now this is going to be copied over to register b. So as before, this again takes up 2 machine cycles, one opcode fetch, one memory read, because m is nothing but a fictitious fictitious register, right? It is just pointing to a memory address. So when you do such a move instruction, it first needs to do an opcode fetch, then it needs to copy the data from the particular memory address. So now we have a code that copies data from successive memory addresses like that. So if I want to later on change this data, I don't have to change the program. So this is one of the good practices while writing a program. So if you want to change the data, you can just change the data. You don't have to change the program itself. In order to execute your program with a different data, if you have to edit your program every time, It's a bad programming practice, right? So in order to do it in a good programming way, so if I want to change this data, okay, to any arbitrary value, maybe x and y, okay, who knows, I can do that. I can just do that and rerun the program. That data which is being denoted now by x will be copied over to register A, and this data which is being denoted by register value y is now going to be copied over to register B. Okay, so that's going to happen no matter what. Now, of course, I can now say add B. Now this happens to be exactly the same instruction we did earlier, right? Now what does this instruction do? It adds the content stored in register B with that of register A and stores the result in register A, right? So it adds the content of register B with that of register A and stores the result in register A, right? So this is exactly what it did. Okay, now instead, why have we done the program this way? So that we can separate our data from our programming, right? From our rest of the program. So here I have 7, 8 and I have 3, 9. Okay, now I have stored this here on a separate memory block. Okay, and from this memory block, through this memory pointer, this data will be fetched over to register A and this data will be fetched over to register B, and then they are going to be added over, right? So that's one of the interesting things here. Now let me go back, and I told you earlier that instead of if I do it naively, I could have pointed to the next memory location by doing another LXI 3, 4, 5, 7, something like that, another LXI, right? But this is kind of wasteful. We do not do things like that because this is wasteful. Okay, and that is why we use increment operation to go to the next memory location. So this was pointing memory location 3, 4, 5, 6. Now it will be pointing memory location 3, 4, 5, 7, the next memory location. Now what if I really did that? What if I really wrote LXI h, 3, 4, 5, 7, something like that. My goal is now to figure out how many machine cycles it takes. Of course, it's a 3-byte instruction. Okay, LXI would have an opcode, so it's a opcode fetch. So the first machine cycle would do an opcode fetch. So that's 4 clock cycles. Okay. So the next thing it will do is to read this entire data, which is a 16-bit data. Now 16-bit data is read in 2 steps. First the lower order byte is read and then the higher order byte is read. So it will do 2 memory reads. So LXI after the opcode fetch does 2 memory reads, right? So it will do a memory read. Okay, what does it read? It reads 54, right? 57. So this is what is read, and this memory read is going to take 3 clock cycles. Okay. And then it is going to do another memory read. Okay, right? Just like STA instruction, just recall that. So it is going to do 2 memory reads to read this entire thing, right? So this is going to read this one, and this is also going to take 3 clock cycles. So LXI H takes up these many clock cycles, so 10 clock cycles to be exact. LXI H, whatever, right? All right. So if I do that, I would be executing this instruction using 10 clock cycles. And how many bytes does it take? It takes 3 bytes of memory. Okay, in the program, right? In the program, it takes up 3 bytes of memory. So it's a 3-byte instruction taking up 10 clock cycles. Got it? LXI H, something. It's a 3-byte instruction, takes up 10 clock cycles. So 3 machine cycles, individual machine cycles. Okay, but I could have achieved the same purpose with INX-H because the whole goal was to increment the value of the HL register pair from 3456 to 3457 so that it points to the next memory address. So I did that through INX-H. Now INX-H is a 1-byte instruction and takes up only 6 clock cycles. So I am both preserving memory as well as number of clock cycles I need to execute an instruction, right? So INX-H is a better option compared to directly doing LXI once more. Okay, because if I do LXI 3457 once more to increment it manually, what happens is I am wasting 3 bytes of memory instead of just wasting 1 byte, right? This takes up 1 byte of memory just to write the opcode. And if I do AXI H, 3457, it would take up 3 bytes of memory. So I am wasting 2 bytes extra, as well as I am wasting 4 clock cycles. Okay, additionally. Okay, this INX instruction takes up 6 clock cycles, but LXI H would have one regular opcode fetch and 2 memory reads. That way, it has an entire, it actually has total of 10 clock cycles. So that will be wasteful of programming, right? So we do not do that. Unless I am, for example, if you ask me, in which situations or which scenarios would you specifically do something like this? Once more, would you do an LXI H, something? You would do that if this number is stored in some other memory location, right? Maybe this number is stored at memory location 5133. Okay, so one of the numbers are coming from this memory location. Maybe the other number is coming from a completely different memory location, right? So INX wouldn't really work here, right? If 2 numbers are stored in completely different memory locations, okay, in that situation, INX will not work, because INX only works because all the numbers are stored in consecutive memory locations, so that you can just increment the HL register pair to point to the next memory address. You can increment HL register pair to point to the next memory address, and so on, keep on going like that. But if the numbers are stored in completely different memory locations and you still want to point them through the memory pointer, then you shall have to do LXIH repeatedly. Okay, so that's one of the scenarios where you cannot get rid of this LXIH instruction. But if the numbers are stored in consecutive memory location, you can get away with this. You can just increment the HL register pairs value. So now that the HL register pair is containing 3457, and subsequently M is pointing to the data stored in memory address 3457, right? That's understood. So we are preserving both memory space as well as time, number of clock cycles. All right. So the result now is the addition between these two numbers. Again, this could be anything. The moment I want to change these two numbers, all I have to do is to change these two numbers, right? I do not have to modify my program at all, right? So with that said, now if I want to store the number at some point, okay, at some memory address, okay, you have seen instructions like this. So in earlier, so if I wanted to store the result, so we ran this instruction STA. If I want to store the result of the accumulator, we use the instruction STA. What does STA do? STA stores the content of the accumulator to a certain memory address. Maybe I want to store the result at 3458. So what does the STA instruction do? Again, we talked about this in our last class. Okay, STA stores the content of the accumulator into this memory location. Again, STA has one opcode fetch, 2 memory reads to read the memory address, okay, and then 1 memory write. Okay, so it takes up 13 clock cycles. In any case, STA does what it is supposed to do. It stores the content of the accumulator. What is the result of the previous instruction? So after doing the previous instruction, what did we do? We just added the content of register B with that of register A and stored the result in register A, right? So register A is containing the sum of these two numbers, and we wanted to store that in this memory location. We could do that through STA, right? Through STA. But STA is again a 3-byte instruction taking up 4 machine cycles and exactly 13 clock cycles. We could do that here as well. We could have written STA and store it at 3458, right? So the result would now be stored in 3458, this memory location, right? But we could achieve this in a slightly more elegant fashion. Okay, and what do I mean by elegant fashion? Let me show you. We can make use of the memory pointer and do the storing thing entirely through memory pointers. So instead of naively and crudely writing STA here, we could do something slightly more interesting. So instead of doing this, we could do increment H once more, right? So what was the value of the HL pair here? At this point, initially the HL pair was stored having 3, 4, 5, 6. So it was, so memory pointer was pointing to the memory location 3, 4, 5, 6. Now here HL pair is being pointed to 3, 4, 5, 7. Now after doing one more memory increment, okay, HL pair is now pointing to 3, 4, 5, 8. Okay, so where is the memory pointer pointing to? The memory pointer is pointing to this memory location 3, 4, 5, 8, right? Now what if I do something like this? What if I execute an instruction that does this? Move m comma a. If I say move m comma a, okay, if I say move m comma a, so what happens? Can anybody tell me in the live chat? I know you have been patiently waiting because we had internet issues, right? But yeah, tell me. Question: where is the memory pointer pointing to? Where is the memory pointer pointing to? The memory pointer is pointing to this memory address, right? This is where the memory pointer is pointing to, right? Because the value of the HL register pair is now 3, 4, 5, 8. So where is the memory pointer pointing to? The memory pointer is pointing to 3, 4, 5, 8. This one, right? Since the memory pointer is pointing to 3, 4, 5, 8, now if I do move a comma m, what is it doing really? It is trying to move the content or copy the content of the accumulator register A into M. But what is M? M is nothing but the memory address here. It is pointing to this memory location. So if I do move M comma A, what does happen? It takes the content of the accumulator and copies it to register M, but register M is not an actual register. It is just a pointer pointing to a memory location. So it does an opcode fetch to understand what it needs to do, and then it does a memory write. So what happens is it copies the content of register A into this memory location. So if this was data X, if this was data Y, then this stores X plus Y, because we added the content of register B, which was this, with the content of register A, which was this, through this add instruction. And then we incremented the memory pointer to point to the next memory location, and we stored the content of the accumulator into that memory location. So that memory location will now have the result of the sum of these two numbers. Okay, so that is what we could do here directly, or we could just use the STA instruction. It's not as bad. Okay, we could use that, but this is one of the uses of move instruction along with the memory pointer M. So in case you have any query, feel free to ask how this things work, and please confirm if you have understood. Please confirm if you have understood. Or if you have any query, feel free to ask. Right. Please let me know if this is clear. Again, please let me know if you have any query, or I shall move on to the um, actual thing here, right? So let's see. Okay, so you people have confirmed that it's understood. So okay, let's look into how we can actually do the same thing through the 8085 emulator we have here, right? So again, we are starting with the preprocessor directives. Okay, so we are going to write our program from memory location, say for example 8050. So we are going to say origin of our program is 8050. So the memory location from which we are writing our program is 8050. Okay, and we have to set the initial value of the program counter with the begin keyword or begin directive. So this is the initial value of the program counter. So this sets the program counter, and this sets where we are writing the program from, right? So we are doing LXI H comma, what was the memory location? 3456, 3456. Okay, then we are doing move A comma M, then we are doing INX H, then we are doing move B comma M, add B, INX H, move M comma A, and of course we end our instruction with a halt. Okay, that's our program. Okay, so now HL register pair will be having a value of 3456. So M, which is the memory pointer, look at this one, all the registers can be seen here, and M is the memory pointer. Okay, that will be storing, keeping track of the that's responsibility of this memory pointer is to track what data we have stored in the memory location pointed by the HL register pair. We have talked about this a lot right now, right? But where are the data? Where are the data? Now the preprocessor directive, or the assembler directive, the assembler directive for storing the data. So you individually store the data separately, right? So the assembler directive for storing the data is with db. Okay, so if I say hash db, then it stands for data bytes. So we are storing data bytes. So what numbers do I want to store? I want to store the data 7. I want to store data 78 and data 39. Okay, so this is again an assembler directive. Did I say preprocessor directive? Sorry, yeah, this is assembler directive. Okay, and now I have to tell tell the assembler that I want to store this data on memory location from consecutive memory location starting on 3, 4, 5, 6, right? So I am saying org 3, 4, 5, 6. Try to understand what we just did here, right? So what we did here, try to understand. Again, db stands for data bytes, huh? So we wrote the program. Our program resides from memory location 8050. Okay, so our program is in consecutive memory locations starting from 8050 memory location, right? And our data is stored in consecutive memory locations starting from memory location 3456. So this 78 is stored in memory location 3456, and this 39 is stored in memory location 3457. Okay, so you get the idea of the entire assembler directive here. So we are using assembler directives to store everything, let the microprocessor know about everything. And this you would do in a proper microprocessor. You would do this by manually going into this memory location and storing the data, then incrementing the memory location and then storing the next data, and so on. So please let me know if this is fine. Okay, so we have stored my program starting from memory location 8050. up to how much memory it takes up to the halt instruction, and then we stored my data starting from memory location 3, 4, 5, 6. Right. So the objective of this subject, or the way I am teaching, is to give you a complete idea of everything. Okay, not some overall vague ideas, but I think this is understandable, right? So let's assemble the program. Again, if you have any query, feel free to ask. So we've assembled the program. Okay, the assembler directives are not visible, right? So these are the instructions. Look now very carefully. We have the LXI H, 3456 instruction. Okay, what does it do? Of course, it sets the memory pointers to HL register pair to the value of 3456. So LXI H has an opcode of 21, and then 3456 would be having a little endian byte ordering. So 56 will come first and then 34. It's called a little endian byte ordering. So it's a 3-byte instruction. And how many clock cycles does LXI take? It takes up 10 clock cycles and 3 machine cycles. 1 opcode fetch, 2 memory reads. We discussed this already, right? Then we have move a comma m, right? So we are copying the content that is being pointed by m, okay, into register A. So it has just one opcode fetch. It has just one opcode, right? It is a 1-byte instruction, but it has 2 machine cycles. So why 2 machine cycles? Because it is doing opcode fetch and that opcode fetch is being followed by 1 memory read, because m is not internal to the microprocessor. M is just pointing to a memory address in the memory device, and memory device is external to the microprocessor. So the microprocessor will have to do a memory read machine cycle to read data from the memory device. So move a comma m has 1 opcode fetch, 1 memory read. So although it is a 1-byte instruction, it has 2 machine cycles. 1 opcode fetch, 1 memory read. Opcode fetch is 4 machine cycles and memory read is 3 machine cycles. So it has a 7 machine cycle operation. Then I have INXH, and I told you earlier that INXH takes up 6 T states or 6 clock cycles. Each T state is basically a clock cycle. So INXH takes up 6 clock cycles because it's a special opcode fetch. And for this opcode fetch is very similar to the standard opcode fetch we know, at least up to the 4 clock cycles, and the rest is actually known to Intel only, right? So you understand this, right? Right. Similarly, so I incremented H, so now HL pointer would be pointing to the next memory address, and then from the next memory address, then data is again copied through move B comma M. So M is again pointing to the next memory address, content stored in memory location 3457, and that data is moved to register B. So let's see that in action. Okay, but before I see that in action, look at all the hex code, right? So this is the total program for LXI H, 3456, opcode for LXI H, and this is 34, this is 56, right? This is the opcode for move A comma M. This is the opcode for INXH and stored in these memory locations, right? So now my program starts from memory location 8050 and ends at memory location 8059. So now if I do a memory inspection, look carefully, my program starts from memory location 8050, right? So in my memory location 8050, I actually have the opcode of LXI H residing. Then the next memory location, next to memory location, we have 3456. In again little endian byte ordering, we have the 3456, this memory address, right? So this is the thing. So my program starts from memory location 8050 and ends at memory location 8059 with the halt instructions opcode. So what is the opcode for the halt instruction? That's 76. That's the end. But look at the 2 other memory locations we also have. We have memory location 3456 and memory location 3457. We have memory location 3456 and memory location 3457, and in memory location 3457, what have I stored? I have stored the data 78, and in memory location 3457, what have I stored? I have stored the data 39. How did I achieve that? I achieved that through this instruction. We again changed our origin to memory location 3456, and through the data byte assembler directive, we stored 78 and 39 in those memory locations. So in those memory locations, I now have this data. So this is my data, and so in these two memory locations, I have my data, and the rest of it is the program. So anytime I want to change the data to add up two different numbers, I don't have to do anything with the program. All I have to do is to change the data. So the data will change and automatically everything will work. So let's run the program. Okay, let's run the program. Let's run the program. And again, if you have any query during my discussion here, and again the discussion will end shortly, you have, I mean, we people have wasted like more than 20 minutes with the internet connectivity issue. Right, so let's go step by step. Of course, now the first instruction has been executed, LXI H, 3456. Look very carefully. What does the H register have? It has 34. What does the L register have? 56. So what is the HL register pair, which is also known as the memory pointer, will be having? 3456. 34 for H, 56 for L, right? So HL register pair has a value of 3456. So it is now pointing to memory location 3456, right? But what does 3456 memory location have? Memory location 3456 would have a data of 78, right? And that is now being pointed by the memory pointer, right? This pointer is now pointing to the data stored in that particular memory location, which is now being pointed by the HL register pair. So this is the data, right? So this is the reference to the data. Okay, so this is just like a pointer in C, right? For example, so M now contains, is actually pointing the data 78. It does not contain that data yet. Unless I do a move instruction, then it will read and copy it over. Okay, so it now is pointing to that data 78. Okay, but it might give you an idea that it is already copied over to M. No, nothing is copied over to M. M is just pointing to that data. If I do a move instruction, it will now copy the data by a memory read instruction, memory read machine cycle, right? So next I am going to do move A comma M. Now move A comma M will copy this data, okay, through a memory read into the accumulator. Okay, and that has been done. So this data has now been moved onto the accumulator through a memory read. Okay, all right. So let's now increment the value of the HL register pair. So the HL register pair is now storing a value of 3456. So when I execute the next instruction, which is INX H, the value of the HL register pair will become 3457. Let's see that. Yes, it happened. So the value of the HL register pair is now 3457. Okay, and look at M. What is now M pointing to? M is now pointing to the next data. So what is the next data? Next data is the data stored in memory location 3457, right? So M always points to the data or refers to the data stored in the memory location pointed by the HL register pair. So the HL register pair now has 3457 in its value. So the memory location pointed by this memory referral here is 39, which is actually stored in memory location 3457, right? So we have this referred to by the pointer M, right? So now if I do move B comma M, say again, this is not yet copied, right? The software just shows you that as if M has this data. This is not like that. Okay, it has not yet been copied. Okay, the moment I do a move instruction here, it will be copied through a memory read. It will be copied through a memory read. Okay, so if I do that, now I did move B comma M. So the data stored in M, or rather pointed by M, will now be copied over to register B. Now the register B has the data stored in memory location 3457. So now register B has this data 39. All right. So if I now do add B, it operates just like before. It added the content, added this value, which was 78, with this value, which was 39, and added them. The result was B1, whatever, B1. Now we are doing something interesting. We are incrementing HL register pair once again. Okay, so we are incrementing HL register pair once again. So we have incremented HL register pair once again. Now what memory location is it pointing to now? It is now pointing to memory location 3458, right? Now what is the value of the memory pointer? It does not yet have anything in memory location 3458. Look at the memory inspector. In memory inspector, you can see there is nothing stored in memory location 3458. Okay, so it's 00 specifically, right? So nothing is stored there. So it does not have any value. It only has 00, right? All right, you get the point. Now, if I do move m comma a, what does it do? It copies the content. Sorry, it copies the content of register A onto the memory location pointed by m. Okay, so m is pointing to this memory location, which is pointed by the HL register pair. So m is referring to this memory location, right? So this is the memory pointer HL. Now the value of HL is 3458. So this is the memory location which is being referred to by M right now. And if I do move A comma M, what will happen? The content of the accumulator, which is B1, is now being will be copied to M. But what is M? M is nothing but a reference to the memory location 3458. So what will happen? What will happen is, through a memory write machine cycle, that data that the accumulator is holding on to will be copied over to memory location 3458, right? So if I do that, that happened. So now, of course, look at the memory here, reference to the memory. It now has B1. But what happened internally? Look at the memory inspector now. Now in the memory inspector, now we have a new memory location where you have something. So now previously we had memory location 3456 and 3457 where we had our data, and through this move m comma a, okay, and by means of incrementing this, we have copied the result from the accumulator onto the memory location 3458, and this is the result. Okay, so this is the result of this move operation. So this move operation copied the data from the accumulator into M. But what was M? M was just a reference to the memory location 3458. So again, please feel free to ask if you have any query. Okay, and of course the next instruction is halt, end of program, end of story, right? So at the end of everything, this data is now stored in memory location 3458. So if you have any query, feel free to ask at this point, because that is going to be our end of discussion today. Okay, I believe how memory pointers work is understood now, because this is used quite frequently, and that is how we are going to proceed learning this programming language, assembly language programming, from things that are mostly used to things that are rarely used. Okay, so this is a prerequisite. For example, I mean, in many of the programs that you are going to do in future would require this knowledge of pointing to memory. Okay, and again, if something is not clear, feel free to ask. If something is not clear, feel free to ask. Again, the handouts will be given to you. You will already have the books and everything, and the programs are already been given to you. Please try to do these things at home, and the video will be available after the stream, of course, with some editing. So I won't be wasting any more time. So like, I'll be waiting here for 5 more minutes. If you have any query, feel free to ask right now. So we shall end that stream exactly at 2 o'clock if you don't have any queries. So again, please let me know if you have understood everything, or if you have any query, feel free to ask. And those who have been present in the live stream but did not write anything on the live chat, please write something so that I get your attendance. Right. So if you don't have any more queries, we shall end our discussion. So thank you very much for patiently waiting here and going through the entire class. Again, if you encounter any query later on at a later point of time, feel free to get back to me through email. I will definitely answer your questions. So I would again strongly encourage you to, install the Java runtime environment and run this tool, run this simulator at your home, and try writing these programs. Try executing this by yourselves. Otherwise, you would not learn anything. Okay. And we shall have our next class on Monday. So we shall continue from where we are leaving off today. Okay. All right. So thank you very much for joining the class today, and I shall see you on Monday. Thank you.